Proofs are actually very important. It trains your rigorous, logical thinking.
Proofs are like writing code. Proofs are like writing code.
It's like writing code, except it's even more rigorous. Because you cannot really test it. You cannot just feed test cases through it. The steps have to follow, one after another. Yikes.
But if you write your code like you're writing a proof, then you know it's going to handle cases that you didn't even test. You can be more confident.
Right. Exactly. Well, at the least, if you design your program thinking about proofs and stuff like that, it'll be easier to debug the program because you're thinking in a very rigorous way and structured way, so your program will be easier to debug. It's really not about who can write programs without any bugs. It's really about who can debug programs or design programs that are easy to debug.
Like you said, how many errors do you introduce for each one that you fix?
That is the key. And a part of that depends on the tools too. Some tools allow you to design programs better, and other tools do not. But most of it is really just programming discipline. How do you think about the program? How do you structure your program? And just don't take any shortcuts. Shortcuts are the worst. I mean, if anyone takes shortcuts in programming, it will save you some time, with that particular logic, but it will just bite you later, to no end.
I just compile and pray.
And of course, the debugger is the other thing. Don't use printfs to try to debug your programs. Use a debugger instead. Put a breakpoint somewhere, make the program stop, look at the variables, and then continue execution as long as everything seems to be fine. You just keep going, single step, check everything along the way.
And you get a list of variables in a function that you're in a GDB.
In GDB?
Yeah, if you put a breakpoint and you're in a function, how do you get a list of variables inside that function?
I do not know because I usually just read the source code and find out which one I want to take a look at. I think there's a way to watch it. In other words, every time the program stops, it prints out the values of the variables that you're watching.
That's display.
Display? Okay. Thank you.
So why don't you like to use printf statements to debug?
Why don't I? That's not me. I'm not Ubuntu, so.
It's Ubuntu.
Because when you use there's only one case where printf can be useful is when you redirect all the printfs from the output of your program into a file, because then you can backtrack and you can actually see how the values change. But that only applies to very few types of programs where it doesn't require interaction. I wrote programs to do motion control using stepper motors, and because it has no feedback, you can just kind of dump out stuff, and then you can use another program to interpret the output of this program to find out where things went wrong. So those would be the only cases where you can use quote unquote printf to try to debug your program. But for a class like this, since we are not doing repetitions or repetitive stuff like that, I think the debugger would be a much better tool. It also does not require recompiling. In other words, if you suspect that your program is broken somewhere else, you can either just continue to run your program, set up a new breakpoint, or you can just start the execution from the beginning and then put a different breakpoint in your program to make it stop somewhere else. So it helps to shorten the cycle of modifying the code and then debugging.
Right. Okay.
All right. So we are going to start on a new topic today. I think it's really quite exciting because we are starting on sockets. So we'll go ahead and take a look at socket programming.
Yes, thank you.
Now the exciting part about socket programming is because this is also sockets have many purposes in terms of systems programming. But for the most part, it is a mechanism where a program can talk to another program interactively. Yep.
What does wine have to do with sockets? Because I'm trying to run the Old Republic in wine, and it's a socket problem that won't make it work. So what is?
That means wine for some reason has a client-server type of communication because sockets are useful for that sort of thing.
Okay.
In other words, you have one program doing one thing, it's providing a service to whoever needs the service. then you can have multiple client programs talking to the same server program and have the same server program to respond to all these clients' programs. So I'm suspecting Wine is using some mechanism like this. In other words, the program is actually broken up into multiple programs and they all run at the same time.
Okay.
I don't know the source code of Wine well enough to find out, to understand how it is broken up, but if it uses sockets, that's probably what's happening. Okay, so socket programming is here, it's under the same, topic. I really should be reorganizing the topics a little bit here, but it's under the same topic, right below raw extension to access. This is really quite the opposite of what we have been doing, because in terms of accessing a extension to a file system, for the most part, it's tedium. It really is a lot of tedium, looking up the offsets, how big is one item, and but the only abstract concept is really just to follow the block numbers. Once you understand, the super block, will tell you important parameters of the file system. You can then locate the block descriptor table, and then from there you can go to the inode table of the block descriptor table that you want to access, and then from the inode table you can access the inode structure. From the inode structure you can locate the data blocks, and then within the data blocks you have to interpret using the linked list process, and that's about it. Okay, so there's a lot of tedious stuff going on, but in terms of concept, it's really not that complex. Okay, it's really just following the pointers along the way. With socket programming, it is a little bit different because, first of all, we want to understand what is a socket. It is definitely not analogous to a socket like a wall socket for electricity, because in this case, a socket is I think I talked about this a little bit last time. It's usually broken up into two types. Okay, you have a socket on the server side, and then you have a socket on the client side. So maybe it is helpful to first make sure that we understand the terminology. What is a server and what is a client? Okay, so what we'll do is we'll just use web serving as an example. Okay, this is just a quick example. I'm not going to record it using the whiteboard. Using the computer. Instead, I'll just use a whiteboard for this purpose. Okay, so in the case of a web server, okay, you have a single web server. Okay. And a web server is just like someprops.org or d2l.lostreels.edu. It's a website, okay? And a web server is basically, in this case, a program that is going to respond to requests. Okay. What about a client? What do you think a web client looks like?
It's just a box, some type of computer.
It looks just like that because we are using a web client. So a web client is really just a fancy name for a web browser. But in the terminology, it is important to understand that this is called the client and this is called the server. So I'll just say that this is someprops.org, and this is your computer on your browser. Okay. We do okay so far with the terminology. We're not referring to machines, we're referring to programs. In other words, this is Apache running on a particular machine. This is Firefox, Google Chrome, or Internet Explorer running on your computer. We do okay so far with those terms. Okay. So, but your computer or your Firefox may not be the only web client trying to connect to the web server, right? So there will be somebody else's machine, another web client, and so on. In fact, you can have many, many web clients all over the world trying to go to the same website at the same time. Are we doing okay so far with this particular picture that you can have multiple clients trying to talk to the same server at the same time? Yep.
Okay, just out of curiosity, if they're all using the same port to communicate back and forth, are sockets how that port doesn't get clogged?
There is an instance of time where the port can be clogged. Okay, so we'll talk about that. Okay, we'll talk about it. But I just want to make sure that people understand the general terms of what is a server, what is a client, and what is the big deal of this socket concept. The socket concept basically allows all the browsers to be talking both ways at the same time. In other words, all of these browsers can be doing two-way communications with the web server all at the same time. Okay, so we are not talking about serving one web client, change to the next web client, change to the next web client. We are talking about having all these connections simultaneously. Okay, now that's a pretty useful concept. Because, have you guys heard of SaaS? It stands for Software as a Service. In other words, we are moving away from having to install software on each computer. Instead, we are trying to run applications remotely on, guess what? Mostly a web server.
Is that cloud computing?
It's related to cloud computing. Cloud computing provides the infrastructure so that we can have software as a service implemented inexpensively. You can do SaaS with a dedicated server, but if you put it on the web, on the cloud, it is just so much more economical. Okay, and a prime example of that SaaS thing is Google Documents. Okay, you don't keep your documents on your own machine. You don't even install anything other than a web browser on your own machine. So you can imagine all these millions of people trying to interact with Google Documents all at the same time, and the interaction is all done by sockets. Okay, so go ahead.
So could you use that same concept like on an intranet, so that you could install your software in one single location, and then everybody in the company can just access it that same way?
There are two ways. What you just mentioned. There are two things that can make that happen, and those two methods are one is actually closer to the conventional method, and the other one is closer to SaaS. The first method is to use a network file system. In other words, you install OpenOffice once on a particular machine, and you make the installation readable to all the people in the organization. So in that sense, you're just kind of using the same concept of installing the software on the machine, except the file system remaps a remote file system onto your local computer. But as far as your computer is concerned, it is still running the program locally in this box. SaaS means you're not even running the program locally. Your local computer is doing nothing more than just JavaScript stuff, relaying all your interaction to the remote server, which is even better because in that case, the processing requirements or the processing resources requirement of your computer, you only need this much, because your screen can only update so quickly. Your network bandwidth is also limited. Whereas if you want to run OpenOffice locally, even if the installation is somewhere else, you still need to have that much memory, processing resources, and so on, in order to support the software. So are we doing okay with the concept of sockets? Now the concept of socket can also be shrunk. In other words, instead of talking about the entire internet, having all these web clients installed on different machines all over the world, you can actually shrink the entire setup into a single physical machine. In other words, you have one single program that talks to multiple programs that are running on exactly the same machine. And those are still sockets. So that means sockets is a very useful concept because you can start with a program that only serves to other programs running on the same machine, and then later on extend it to the intranet, and then later on extend it to the internet. Okay, there's no differentiation. A socket is just allowing programs to talk to each other. They do not need to share memory. They do not need to share an operating system. They can be installed on anything. Your web clients, you can have Mac OS X, Windows, and Linux, all different platforms talking to the same server. As long as they talk in the same protocol, everything is fine. So that's basically what the terminology is. A client is the one that makes the request, and the server is the one that answers the request. In other words, if there are no clients making requests, a server is just really sitting there doing nothing. So are we good with the terminology? Who is a client and who is a server? The server waits, the clients make requests first. Now, once we establish, okay, a socket represents a communication endpoint for either the client or the server. So when we talk about the socket, it's kind of ambiguous because we don't know which end we are talking about. Now, when the two endpoints connect, then two processes can communicate using just regular file operations. In other words, you can then use read and write functions for two programs to talk to each other.
So that means you're interacting with standard input and output, right?
You can if you want to. In Linux and other type of Unix type operating system, there is a program called what we call a super server. inetd and xinetd are what we call super servers. And the concept of a super server means you can actually write your own server program, but not having to understand sockets at all.
Why would you do that?
Because it's easy.
Oh, okay.
Because all you have to understand is standard in and standard out, and then and if you know the protocol for a particular communication protocol, you can just you can then implement your program. You don't have to understand sockets in that case. But it's not very efficient because it starts up one process per communication channel, so it's not very efficient. Now, what is unique about sockets is the communication process is divided into servers and clients, so we talk about that in the picture. While a process can be both a server or a client, server-type sockets are different from client-type sockets. So we'll go ahead and take a closer look at first server sockets, and then we'll take a look at client sockets. And the last paragraph is sums it up. Sockets are a special mechanism that permits a single server multiple client application to use normal file operation so that the communication of the server and the client programs can be done. Are we doing okay so far with this slide? It's just mostly concepts. There are no function calls. Well, there are two function call references, but they're just basic read-write operations.
Do you have to have multiple clients?
No, you can have zero client, which means the server is just sitting there doing nothing. You can have a single client, which means you have just two programs talking to each other, or you can have 200 programs trying to talk to the server at the same time. The key is they can talk at the same time. There's no need to finish one conversation before you start the next. Okay. Now this is different from pipes. Okay, most of you already know how to use a pipe. A pipe is kind of like something like this. Okay, PS-AF pipe to less. The symbol, this vertical bar symbol, is called a pipe. But a pipe is a very limited and restrictive concept compared to a socket in many, many ways. First of all, the direction is only one way. In this particular case, the direction is the output of the PS command will only serve as the input of the less command, but it's only going one way. The second limitation is they can only happen on the same machine. In other words, in this case, PS and less, they have to run in the same operating system in order for this to work. Okay, there's no way I can do this remotely. You can do it sort of remotely if you can actually do a pipe and do something like this. You can pipe it to SSH, but that's really not a concept of sockets applied to the pipe. It's actually SSH doing the socket concept, but it's not really the same thing as a socket in this case.
What would that do if you piped it to SSH?
Then whatever PS-AF generates becomes what you quote unquote type in the SSH command.
Oh, okay.
Because you can say SSH user at some server.com, and then you can use double quote to include a command. So the command inside the double quote can be something like cat to some file.txt. So if you run the command like this, then the result of the listing of processes on your local machine will be captured by some file.txt on the remote machine. So it's a handy way to do certain operations for in a Linux type environment. Okay, so let's move on to the next slide, and we'll actually start to see some coding. All right. A server endpoint. So we'll start with a server endpoint because it doesn't make sense to start with a client. You have to start with a server, so that someone is waiting for a communication attempt. Then we can talk about how do we establish a communication channel. A server, in this case, is not a machine. We are referring to a particular program, a process in this case, which is a program in execution that is waiting for other processes to connect to it. As such, a server communication endpoint needs to be made known to client processes. Okay, so let's just kind of focus on this particular sentence and make sure that we understand what it's saying. Okay, first of all, I know this is only one sentence, but there are terms here that can be confusing, and they are actually technical. First of all, what exactly is a process?
It's a program in execution.
It's a program in execution, but it is not a thread. Okay, when we talk about multi-threading refers to multiple execution quote-unquote fronts inside a process. A process is a program in execution. Now, you can have multiple processes of the same program running all at the same time. There's nothing wrong with it. In other words, a program is equivalent to a class in C++, whereas a process is more like an object that you create out of a class in C++.
Well, then why is it that Firefox will only let you start up one Firefox at a time?
That is not the case, because you can use a -- profile and actually start up multiple instances of Firefoxes at the same time.
Okay, so it's an issue with Firefox, not a process.
It's a problem with the profile, because if you start up if you only use one single profile, which is the default profile, Firefox understands that and go like, well, but you have me running already. Why do you want to start me again? I think in the case of that, Firefox would actually just start up a new window, but it is sharing the same profile as your, which is still using your default profile. It actually does allow you to start up multiple times, but it may not register as multiple processes because Firefox uses the same process to serve multiple windows, which is bad in a way, because if you crash one, the whole thing.
So that's how Google Chrome does the sandbox thing then, right?
I do not know exactly how they do the sandbox thing, but I know Internet Explorer actually starts new processes every time you start a new one.
Okay.
Yep.
One of the founding things of Google Chrome that made it different was specifically that every tab was by default a new process.
Okay, so you do end up with multiple processes, whereas with Firefox, it's a single process serving all the different tabs and all the different windows.
And in fact, tabs can crash in
Yes.
Chrome.
But without crashing the whole thing. You can crash
Exactly,
one
just
tab
tab
without
crash.
closing the whole thing. And the same thing in Internet Explorer too. I know in Internet Explorer, when you double click or when you click the Internet Explorer symbol, it starts a new process every time you click it. So we'll talk about multi-threading versus multi-processing. The pros and cons of each approach later on when we get to multi-threading. But it does make sense. The first paragraph makes sense because before you can even communicate with a server, you need to know, where do I find the server? Okay, what is the address of the server? There are two types, or at least two ways to find a server. One way is to use the network method, which means you have an interface, which is 192.168.3.25. That's called the interface or the IP address of a machine. And in this case, you have port 80 referring to a particular quote-unquote port that you want to talk to on that particular interface. Now, the term interface is actually important because each machine can have multiple interfaces in networking. Now, this is not a networking class, and I do not intend to turn this into a networking class. But one thing you can do, if you're curious about this sort of thing, is to run ifconfig. Okay, sbin/ifconfig, and this
Why do
is
you have to
telling.
use sbin? You could just invoke. Oh, because you're not.
Because ifconfig is not on the path of a normal user.
Okay.
But even though the program is executable by a normal user, it is not on the path of a normal user. So in this case, I have two interfaces already. One interface is the 165, 196, 100, and 103, which is a interface that other machines can see. The other interface is 127.0.0.1, which is also called loopback or localhost. That is not visible from the outside. It's only visible from the inside of this machine. But there are two interfaces already. So when you specify a port or an endpoint for communication, you have to specify how other machines can see you, and most of the time you should specify both the interface as well as the port. Are we doing okay with this? Okay. So this is one way, but in this class, since this is not a networking class, we're not going to use the networking approach to define a socket or define the address of a socket. In this class, we're going to use named sockets. Okay, a named socket is an entity in the file system. It has an inode. Since we are working on the homework assignment, we should all know about what an inode is. So a socket, a named socket, actually has an inode structure associated with it. It's a persistent thing. When you reboot the system, it will still be there. Compared to the IP address plus port number approach, a named socket is only useful if both the server and client processes share the same file system.
So, hold on then. Okay, because you said it doesn't matter which operating system you're using. So how can that still be true? Because, Macs use HFS, Windows uses NTFS.
Well, in the second approach, it does depend on the operating system because they have to be running in the same files. They have to be using the same file system. I tried this across, NFS and Samba, and it won't work because socket is actually fairly operating system dependent, or named sockets are file system dependent. So in this particular case, they have to be running on the same machine. Okay. So are there any questions so far about this approach? Yep.
Is there any impact to it being persistent? For instance, if you write something to the socket and it hasn't been read by the server, and then, I don't know, the server, the system loses power and it boots back up, the program starts up again, is that essentially acting as a cache, or
No.
Okay.
It's not a cache, it's not a buffer, it's not a FIFO. All that it is basically a marker so that both the server and the client can agree and say, okay, this is a single point that both of us can see. And the server will use this point and say, okay, I know I should be monitoring this point for incoming requests to connect. And then the client say, I know those points, I know where to find that critical point. So when I want to start to communicate, I know where to look for the server in order to communicate. But it doesn't serve anything more than just a marker. All right. So section 4 starts with the server side of the program, and you can see that it's really not a single call because it really is kind of complicated from the server side. The client side is a whole lot simpler. Okay, first of all, on the server side is you have to do a socket call. The socket is both the name of the construct and also the name of the function. Okay, well, since it is the name of the function, you can also use man to socket to read the technical detail of how to use the call socket, how to use the function call called socket. So we'll go ahead and take a look at the man page, and I'll just go ahead and point out the important parts of it. Okay, first of all, you need to include the header files. Okay, but that part is pretty easy. And then the call looks like this. You have to indicate the domain, the type, and also the protocol. And in here, you can see that it describes what the domain is. For us, in this particular class, all we want is to use either AF Unix or AF Local. I believe they are synonymous. They define exactly the same macro. And all that means is we only want to implement local communication. In other words, we're only facilitating the communication of processes inside the same operating system. Yep.
Is there a class we could take where we deal with other operating?
I do not think so, but once you know how to deal with AF local, AF INET, which is IPv4, and INET 6, which is IPv6, they're really about the same.
Okay.
Okay. So.
And can we implement our own protocols? Like say, okay, I don't know, just use an example, like Yahoo has their own protocol, like Y-Messenger, or something like that.
What you refer to as a protocol is actually an application layer protocol. Sockets only deal with up to TCP/IP level, quote-unquote, protocol. So what you're talking about is writing on top of TCP/IP. Okay. So it has no relevance when we talk about the socket call itself. Okay.
So we can't use modified, we can't use protocols other than what it has here, right?
That is correct, but that defines most of the useful protocols already. IPv6, IPv4, what that's the basis of most networking protocols.
Okay.
Okay, and then you have a whole bunch of weird ones too, that I don't even know of.
Apple Talk.
Apple Talk, yes.
Yeah.
Okay, so that's the first argument. The first argument, which is domain, you want domain to be just AF_local because in this class we just want named sockets. We don't want internet IP address sockets. The second one refers to the type. So we'll go take a look at the type here. The socket has the indicated type, which specifies the communication semantics. The currently defined ones are stream, dgram or datagram, sequence packets, raw, packet. So what we want in this class is really stream because it will give you file-like operations when you use stream. The other ones are not file-based. In other words, they are not giving you a whole stream. How many people know what is the concept of a stream in C++? Not in C, but in C++. iStream, OStream, IOStream, that sort of thing?
Okay. I know what they are, I just don't understand them.
Okay. It basically, all it means is, you can, with an iStream, you can read from it sequentially. You can read byte by byte by byte. And with an OStream, you can write to it byte by byte by byte. In this class, we don't use the concept or the word of a stream, but we do use the read and the write system calls in order to interact with the file. Do you still remember that homework assignment, the first one, where you're supposed to read in something and just echo it back out? We're using streams because all we're doing is reading sequentially and writing sequentially. When you use the stream concept, you can use read-write, but you cannot use seek because it is just strictly reading in a particular way in sequence and also writing in sequence. You cannot skip bytes in that case. Are we doing okay so far with the first two parameters of the socket call that we need to use in this class? The third parameter is protocol, and when you look up protocol, where is it? Okay, protocol specifies a particular protocol to be used with a socket. Normally, only a single protocol exists to support a particular socket type within a protocol family. So in this case, we need sockets of sock stream of full duplex byte streams. So in this class, because we are going to use sock stream, full duplex means it is bidirectional. Once you have a communication connected, once you have two programs connected by sockets, both processes can write and both processes can read. Okay? When you write from one, it will be feeding to the other one so it can read. When you write from the other one, this one can read. Are we doing okay so far? Yep.
I don't know if it's relevant, but does that mean that there's no strict client-server relationship at that point because they both are kind of providing a service for the other one? Or is that not true?
They have communication. They have stream-like communication capabilities. But how you want to handle the server-client part is entirely up to you.
Okay.
Okay. So when we get down here, I'm just trying to remember how to specify the third parameter, which is the protocol. I think I have some sample programs later too, so maybe we can just wait.
I saw a function called get protocol about a screen now.
Okay, get proto ent on how to map protocol name strings to protocol numbers. Okay, I think this is the key because only one single protocol exists to support a particular socket type, so you just leave it at 0, which is the default. Okay, so the first parameter is going to be AF local, second parameter is sock stream, and then the third parameter is just a 0. Okay. So the next question, which is actually a more fundamental question, is what does it give you? What does it do? Well, the first sentence explains it. All it does is to create an endpoint for communication, and then it returns a file descriptor of that endpoint. Okay? But what about the IP address? What about the name of the named socket? It's not specified in this call. And you're right, it is not specified. This is the FD or the file descriptor that is returned by this call is completely internal to the server program, to the server process itself. There's nothing published. No one can actually find it at this point. Are we doing okay so far? It is the first call. You have to create this endpoint first. And then later on, we can connect the endpoint to an address, to a place where both the server and the client can see. Yep.
This is kind of a technicality. I don't know why you would ever do it, but I'm just curious. You could, within the same process, technically use that file descriptor to read and write to that socket at that point, right?
Well, right now the socket is not visible from outside, so there's no way to establish a communication.
But as long as, if you for some reason wanted to use that socket inside the same process, you could do it, correct?
No, you cannot. Because this endpoint is not ready to accept communication yet. It's not ready to accept incoming requests to connect yet. So we'll get to that call, when it's not listening, it's not ready to listen yet. So we have to kind of do another 2 calls before we are ready to listen or accept a connection. Okay, so this is the first one. I'll leave this one here. Yep.
Do we have to close or open the socket? I mean, you have to set it for listening. So
Running
it's like
socket.
opening it,
Okay,
right?
socket is the same as kind of open. It creates the endpoint. Okay, so it's kind of like open, but it doesn't connect to a particular IP address and port number, nor a named socket at this point. It really is just defining an endpoint. That's all it's defining is an endpoint. So we'll talk about what we're going to do with the endpoint. The second one is called a bind call, which is actually the magic. This is where the magic is. Okay, the bind call. Okay, let's go ahead and use another tab here to take a look at the bind call and to bind. Now this one is interesting because it only has 3 parameters, but the parameters are far more complicated than the first call. When the socket is created with socket, it exists in a namespace address family but has no address assigned to it. In other words, no one can find it. It has no address. It has no identity whatsoever. Bind assigns the address specified to by ADDR, which is the address argument. And you will see that this is not actually pointing to a string. It is pointing to a structure. So we'll take a look at the structure later. It basically binds sock FD, which is the one that we just created using the socket call, to the address specified by ADDR. Address length is needed because the length of this structure is variable, so you have to specify the actual length of the structure. So we'll take a look at the structure later on and see why do we need to specify an address length in this case. It is normally necessary to assign a local address using bind before a stream socket may receive connections. So that answers your question about why are we ready to accept connections inside the same process? And the answer is no, because you need this call to prepare the socket so that it's ready to accept inputs. So this is the structure. This is the sock address structure, which is what you need in the second parameter. The second parameter is a pointer to that kind of structure. The question now is, it refers to yet another structure. Okay, so what is the other structure here? Well, it varies. The rule used in the name binding vary between address families. Consult the manual entries in section 7 for detailed information. For AF INET, which is not what we want here, is IP in chapter 7. And what we only need here is Unix, AF Unix, and we just have to look up Unix 7, which means man 7 Unix. That's what we need to look up.
And that's the same as AF local, correct? AF
Yes,
Unix.
it is the same as AF underscore local. Okay. So we'll keep that one in, running too. So we'll say man 7 Unix. Sockets for local inter-process communication. Now this really gives you, the call that you need to do. The first one is just a socket call. The second one is a socket pair, which I don't think we need in our homework assignments. This is the address format. We have the same structure. It looks kind of the same, but it's not really exactly the same. Okay, there are 3 addresses that are distinguished in this address. The path name. In this case, a Unix domain socket can be bound to a null-terminated file system path name using bind when the address of the socket is returned by get sock name, get peer name, and accept. Its length is offset of this entire structure plus the string length and so on. And then the last one, the second one is unnamed. This is what we need in this class because we're dealing with named sockets. I'll give you, actual coding examples after this because I know it looks, awfully confusing at this point. That's basically all we need to know. I mean, there are lots and lots of options after this, but a lot of the options we don't really need to specify for what we're doing. So we'll leave the details later on. Okay, and in fact, I probably have an example, or I also specify here, how to use it. The second, the bind function is used for this purpose. The first one is the FD or the file descriptor returned by socket. So that part is really easy. Whatever socket returns, as long as it is not negative, specify that as the first parameter. Because we need to say, okay, which endpoint are we going to specify an address of? The second parameter is the address of the address. The first word, the address, is in the sense of C programming. It is an address of a structure. The second one, the address, is basically specifying, where do we find the endpoint. Okay, so that's why it's an address of an address, but it's not the double asterisk type of concept. It's the asterisk of a structure that contains a address specification. Yep.
Even though we're specifying the endpoint of the socket, we're not creating the client socket yet, is that right?
No, the client socket is not created because the client socket can only be created by the client process itself.
Right.
So we are still handling on the server side, we're still preparing the server process to receive connections from clients.
Okay.
Yep.
Do we have to develop 2 programs, one for the server and one for the client?
Well, when we get to the homework assignment part, we'll see that we can use one single program because you can use a switch on the command line. So you can switch the mode of the program from client to server and
But you'd have to be running 2 separate instances
Right.
of the
You have to
program
do-
because they need different processes so they can,
yes. You'll be running multiple processes to test this kind of program. Okay.
What?
If the endpoint is to be associated with a name socket, which is the case in this class, then struct sock addr underscore un should be used as the actual address structure, and use this to read the details of how to specify a named socket. In short, the son underscore family field should have a value of AF socket, whereas the son path field is a null terminated string for the name socket. Let's go ahead and take a look at the last help that we were looking at.
Why was it called Sun Family? Why is it Sun? For like Sun Microsystem?
I think it is originating from the Sun microsystem. Yep. I'm thinking that in this case, the concept of a named socket originated from Sun microsystem, and that's why they prefix it using SUN. Unless SUN is an abbreviation of something that I do not know of.
I'm guessing it might be sock underscore UN abbreviated to.
Oh, okay, that makes sense too. Yep.
Wait, what did he say? Sock what?
Socket, that provides the S, and then UN is Unix.
Oh, Unix.
The,
okay.
So it's a
the
Unix
struct
socket.
Right there, the
Yep.
name of the struct.
So that means we know how to initialize this structure. The first one has to be initialized to the constant AF Unix, and then the second one needs to be a string, a null terminated string of the named socket. Okay, so you need to initialize the structure first before you call this function. It's not this function, the bind function, which is described here. Okay, before you call the bind function. And then you have to specify the address length, because the address parameter of bind is cast to the address of the generic structure, and so we have lost the size information. Okay, let me just bring up the two help files, and you can compare. What you can see what I'm talking about. Look at this structure here. Remember this name. What is it? It's struct sock address. Yep.
Why is it you're passing pointers and not references?
Because this is C and not C++.
Oh, okay, all right, yeah, okay.
Okay. And the bind call is actually really close to the kernel interface too. You can probably do this in a system call, int $0x80. Okay, but look at this this type here, and then we'll switch to the other one, and then look at this structure here. Are they the same name? They're not the same name.
The underscore UN.
This one has an underscore UN for a Unix, AF Unix, for a Unix type socket. So do we have a problem here? Okay, you write a program, you define this type of structure, and then you pass the address of that as this parameter.
Well,
Would
it
that
said
work?
something was cast, right?
Well, you need to cast it because they are of different types.
Yeah.
But the problem is, once you cast it, when you cast the type of a pointer to another type, can you still keep track of the size of the original structure?
Isn't that information lost?
That information
'Cause
is lost.
You don't save pointer sizes. I mean,
Exactly.
you can. I guess you can.
But because
you don't.
But because you lose that information, now you have to specify the actual size of that thing. This is a classic case of how things need to be implemented before we have object-oriented programming. Okay, can anyone identify which concept or concepts in object-oriented programming will save us all the trouble of doing this sort of nonsense?
Is it member variables?
Member variables, but particularly we need subclasses. Okay, we need subclasses and the concept of a superclass. Remember in C, if your subroutine, if your function is specifying the address of a superclass, can you pass something of a subclass to that parameter? The casting from a subclass to a superclass is not only permissible, it is also automatic. But from the superclass perspective, how do we know exactly what type of structure this was originally? Does anyone remember how to do runtime casting in C++? So you can cast a pointer to a superclass back to the appropriate subclass. No?
Oh, we took it from Fox, so.
I never learned that.
You never learned that.
I never learned
Is
that.
that the reinterpret cast?
Huh?
Is that the reinterpret cast?
It's a runtime cast. You have to first check the actual type of an object first before you cast it, because you can cast it incorrectly if you don't check first. Okay, for anyone who wants to know that, I'm pretty sure no one actually wants to know
Does
it.
it have to do with like the virtual classes and things like that? Virtual.
Okay, I think I still have notes on that since I taught 400 once. Okay, so I'll see, look for casting. Up, down, static, and dynamic casting. I think that's it. Up casting, down casting, dynamic casting. So what we are talking here, this is definitely not related to this class. Okay, this is dynamic casting. How many people vaguely remember something that looks like this? Yep. You remember that? Yep. So that will save us save us the trouble from the bind, business. Okay. Let's take a look again, but this time I'm going to use a picture to show you. Okay. Bind can be used for multiple purposes. You can bind a named socket to an endpoint. You can bind an IPv4 address and port number to an endpoint. You can bind an IPv6 interface plus port number to an endpoint. So bind has to handle all these different types of addresses. Okay, is that making sense so far? When you read the bind documentation, that's basically what it's saying. But each type of interface requires different details. With a named socket, it's pretty easy. Just give it a null terminated path to the named socket, and that's all that we need. But when you want to specify an IP address, what do you think you need to specify? An IP address and a port number. Okay? So the format, the actual format of the details can be different. So what bind is doing is when you look at the structure, okay, let me just switch back to the structure here. When you look at a struct sock the ADDR construct here, it always has the family as the first member of the struct. That is the key because it identifies what type of address we're specifying, and therefore it tells bind how to interpret the rest of the structure. Okay? It's not something that you normally do with a C or C++ program, but this is actually done not by your program, it's actually done by the kernel. All this information is actually passed to the kernel, and that's why we are not going to use C++ concepts in object-oriented programming, because the kernel is a very low-level structure and low-level code, and it doesn't understand those concepts in C++. Yep.
So that's the same out of all those socket structures?
Yes. One thing is common. It always has an integer as the first member, and therefore the first one will identify what it is, and therefore how to interpret the rest of the structure. Okay? So are we doing okay so far with the bind call? Yep.
Since we're specifying the endpoint address, does that mean only that endpoint can ever use that socket, or can still multiple clients come and use that?
Multiple clients can see the same endpoint. They can all say, oh, I want to connect to that named socket.
Okay, so when you're specifying the address, the endpoint address, that's still just within your same operating system?
Correct.
Okay.
So in this case, because we're dealing with a named socket, all you have to do is to specify, let's say, /temp/socket1.
Right.
Okay, that's kind of like a normal file name,
And
except
all
the
the
type
clients
of the
come-
file is not regular. It is actually
Socket.
identified as a socket.
So then all the clients come to that endpoint.
So all clients who want to connect to the server can now say, oh, okay, I want to connect
Socket
to
one.
that address,
Got it.
which turns out to map to the endpoint that is represented by a file descriptor from the perspective of the server.
Okay, that makes sense. Thank you.
Okay. Okay, so we're almost there. Okay. Okay, then we're ready. Okay, once we are done with the bind call, then the server can say, okay, now I have an endpoint. The endpoint is attached to an address that other people can see. I'm now ready for business. I'm listening. So the listen call is interesting in one way, is that it may not return immediately. In other words, it won't come back until somebody is trying to make a connection.
So it'll just idle there.
It's not idling, it's sleeping. Okay? So technically speaking, it's not, there's no, a process has quote unquote no idle state, it has a sleep state, which means there's nothing to do, I'm just waiting for someone to connect to me, and therefore it doesn't even consume any processing resources. It takes up RAM because the program is still loaded, it's actually still running, but it's in a sleep state, which means it's not taking CPU cycles. Okay, the listen call takes two arguments. The first one makes sense. It takes the endpoint file descriptor from the socket call. The second one is called backlog, It specifies how many pending requests, is an integer. It specifies how many pending requests from the system can queue up. Okay, let's take a look at this, what we mean by this one here. This little sentence here. The second parameter defines how many pending requests the system can queue up before a client program will get an error. Okay? But we just said that we want to allow multiple clients to connect to the same server in the case of a socket. So why do we have to deal with something like this?
Because you only have limited resources on the server side.
Exactly. The server program itself may execute slower, right? Because of the system load, it can be running slower. So that means if you set this number to, let's say, 1, okay, if you set the backlog to 1, and for whatever reason, your program takes a long time to process the last listen call, you can have multiple clients try to connect during that time. So if you set backlog to 1, that means I can queue up one client's pending request to connect. But then when the second one comes in and say, I want to connect to the same endpoint, the operating system, not your program, but the operating system will reject the attempt to connect and reply back to this web client and say, connection refused. Okay? So the backlog allows you to specify, how many of these pending requests can I queue up. Each one will take up some system resources, so you don't want to set that to a huge number, but you have to set it up to a reasonable number. Okay. Now listen, like mine, returns 0 when it is successful. So how many file descriptors have we got so far with the server-side socket? Only one, the endpoint. Okay. The first call, which is socket, creates the endpoint, but it doesn't have any address attached to it. So nobody can find it, the server cannot even listen to it. The second call, which is the bind call, attaches the endpoint, which is completely internal to the server process, to an external address that everybody can see. All the clients should be able to see the address. It can be a named file, a named socket exists in the path. It can also be an IP address, depending on how you want to set up your socket. So now we have, after the second call, we have an endpoint, which is the server's internal structure. We have an address that external programs and other machines potentially can see, but we're not ready yet because the server program is not saying, oh, okay, who wants to connect? The server program at this point just has an endpoint and an address. It's not doing anything with it. The third call, which is the listen call, is the server saying, okay, I'm ready, I'm open for business. I'm taking orders now. So now the server is actually quote unquote blocked, which means if no one wants to connect to the server will never return from the listen call. Are we doing okay so far with that concept? Yep.
When you said, I just want to go over that again. You said we have one file descriptor despite these 3 function calls so far.
We're using the same file descriptor in all the other 2. The first one creates a file descriptor.
Right, the integer return of the socket
right.
function call.
That's the only time we are generating a new file descriptor or using a new file descriptor. The second and the third call basically reused the same endpoint because the second call is just attaching the endpoint to an address, and then the third call is saying I'm open for business using the same endpoint. Okay. The next one is going to create another file descriptor. Now this time it will get a little bit confusing. After you listen, after listen returns, now when listen returns, what does it mean?
Client.
All it means is somebody was trying to talk to me, but I have not even accepted the connection yet. Okay? Let me say that again. When listen returns from the server process, all it means is we have at least one connection attempt that is pending. Okay? Now the server can decide what to do with that request to connect. There's no connection yet. There's only a request, at least one request to connect pending at that point. So now the server typically would say, okay, I accept this connection. So the accept call will take the same parameter as bind. However, the accept serves a very different purpose. This means whatever parameter you pass to bind, we have talked about that already, you have to use exactly the same parameters for accept. What accept does is it will extract the first connection request that is queued up to the endpoint identified by the first parameter, which is the communication endpoint. If there's nothing queued up, then the call is going to be blocked. Okay? But since you just came back from a listen call, it means you should have a pending connection at this point. When you look at the return value of accept, what do you think it is going to return? Some of you can read really fast and you can
File
tell me.
descriptor?
It returns a file descriptor. Would that file descriptor be the same as the endpoint file descriptor?
No, it's the client's endpoint.
Well, it's not the client endpoint, but it is a new file descriptor. Okay, so now we have two file descriptors. The first file descriptor that we created using socket is the file descriptor of the endpoint. The file descriptor returned by accept is the file descriptor of the stream itself in this case. Okay? Is that concept okay? The endpoint descriptor is not useful for communication purposes. It's only useful for, okay, who wants to talk to me? It's only good for that purpose. I'm only listening and waiting for people to connect to me, and I can decide to accept a connection. But once you accept a connection, the socket, the quote-unquote socket endpoint, is kind of like a class again. It is used to stamp out a new object. The object is this new file descriptor that is returned that you can use as a stream. So the second file descriptor returned by accept, you can use read and write on it. But the first file descriptor, which is your endpoint, you cannot use read or write on it because all it does is to identify an endpoint so that people can make requests to connect to this particular program. Yep.
So the first file descriptor is like your telephone line, and then the second one is the actual communication port that will occur.
Yeah, the first one is just so that you can listen and accept.
Right, it's
The
just
second
tapping on
one,
your shoulder.
yep, and then the second one is the one that you can read and write from. Read from and write to. Mm-hmm. Okay, then of course there are all kinds of details after this. Okay, first of all, you don't want everything to be blocking because especially in a single-threaded program, if you block, what's going to happen? Nothing's going to happen, right? A blocked program means it's not executing, it's not doing anything. And then there's also accept for function call. It takes 4 parameters, and that's why it's called accept for, because it takes 4 parameters. It takes the same first 3, but it also accepts a 4 parameter called flags. And if you specify sock non-block as the last parameter, then the call does not block. In other words, you can say accept. If nobody is trying to talk to you, it will still come back, and it will just use the return code to indicate, okay, nobody is trying to talk to you. Accept and accept for returns a non-negative value, that is the file descriptor of the connection. If -1 is returned instead, it means an error might have occurred. This is one instance that the global variable error num must be interpreted. Particularly, you want to find out why it is coming back as a -1. Because if this is the case, in either case, error would block or error again. It means it didn't find any queued connection requests, which means it's not really erroneous. It's just that you were trying to you were trying to call accept when nobody was even trying to talk to you.
But why would that happen if listen just waits until it returns when there's a connection that wants to happen?
One potential problem that can happen is between the listen and your accept,
Oh, that's all you had to
the
say.
client decides to give up.
Right. So
So
listen
that-
still returned its 0.
Right.
Okay.
So it is possible that it happens.
That makes sense.
So you have to kind of remember to handle that case.
Okay.
And this paragraph basically just talks about the fact that we have two different types of file descriptors. The first one is only the endpoint, and the second one is the actual stream itself. Okay, so if you set up a loop to listen and accept, how many streams can you create out of this loop here?
Limited.
32,000?
As many as the file system would allow you. The kernel sets an upper limit as to how many file descriptors a process can have. And that puts the upper limit. But basically from the theoretical perspective, there's no limit. You can be talking to a whole bunch of programs all at the same time. Or I should say at this point, you can have connections opened to multiple processes at the same time. The actual communication depends on the read and the write operation. Are we doing okay so far with the 4 calls of the server? Yep.
When you're listening and somebody requests service and then you actually go through and you accept, and there's communication that occurs for a period of time, when does that end? When does that communication end and then another listen to that same client?
Aha! Okay, you are asking a very good question. Let me just rephrase the question so the rest of the class understand the question. Or does everybody understand already and there's no need for me to repeat it? Okay. The question is, okay, let's think about, okay, I'll just go ahead and write it here because I think it's this way we can at least capture it in the video. Okay, so I'll just use mousepad here to describe the process. Okay, so this is on the server side. Okay, on the server side, there are 2 things that you have to do on a one-shot basis. Okay, so these are initialization. The first one is to call socket, and all it does is to allocate an endpoint. Okay, is that okay so far? It allocates an endpoint. There's nothing really you can do with this endpoint at this point. The second thing you want to do is to call bind, and it connects the endpoint to an address so clients can find the socket. Are we doing okay so far with the initialization? Those are the only 2 things you have to do in order to initialize a socket and the endpoint of a socket.
And the endpoint is the file descriptor? Or?
Yes, the endpoint is identified as a file descriptor, yes. Okay, whatever socket returns is the endpoint file descriptor. Okay, so I'll just say here, return as a file descriptor. Okay, so the endpoint is a file descriptor, and you have to use it again and again. Okay, and then per connection from a client, okay, you have to do the following. The first one is you have to call listen. Okay. Let's see. I think listen only needs to be done once. Yeah. So listen is only done once here to basically say I'm open for business. You don't have to say I'm open for business repeatedly. So once you are done with listen, we are open for business. It prepares the endpoint to accept incoming connection requests. Okay? So per connection from a client, the first one is either accept or accept for. Okay? To wait for an incoming request to connect. Okay? When accept returns with a file descriptor that is greater than or equal to 0, okay? Assuming accept returns a non-negative value, the new FD is a stream file descriptor. So now the communication channel is open. The server can write to that file descriptor so that the client can get the information back, or the client can talk on the other side, and then the server can read from this file descriptor to read what the client is saying. Okay. So we have a question. This is on a per client basis. So how are we going to handle multiple clients talking at different speeds?
Won't they all have different file descriptors?
They will all have different file descriptors. But this is only one, this is a single threaded program. We only have one point of execution. Read itself is blocking. In other words, okay, let's say I'm the server. Okay, let's say I'm a web server. And as a web server, I can use the accept call to establish multiple connections to multiple clients. But the clients can be talking very slowly, right? I mean, in order to send out the HTTP request, that request can come over to me in a very slow fashion. Some clients will talk faster, some clients are slower. So let's say, the first client that I'm connecting to is a slow client. Does that mean the fast clients, even though I have the connection already open, will have to wait for the slow client to finish talking before I can surface the faster clients?
Don't they have their own streams?
They have their own streams, but you have a single thread program.
Don't they have multiple processes?
You could fork?
Or you fork?
No, we're not talking about forking here. So we are not forking to multiple processes. We are talking about a single process, single threaded program, multiple client connection. How are we going to do it?
And the stream's not buffered in any way. The stream's not buffered in any way.
The streams are not buffered if you use read. Read is not a buffered call. Okay, even if it is buffered, you can only buffer up to a certain point.
Right.
Okay, so the question is, how can I surface all these clients efficiently so that the faster ones do not have to wait for the slower ones to finish first?
Tell read not to block. Tell read not to block.
Yes, that's the first thing you have to do. And there's no need to even make read not to block. You can have read blocking all you want. What you need is, okay. But that's basically what your question was, right? I mean, how do we handle multiple connections all at the same time when some clients are talking faster and other clients are slower? Okay, so we'll go ahead and talk about that part. It is on the client side. Okay, on the client side, it's pretty easy. Okay, you just say, connect, and when connect returns, the connection is already done. Okay, so that's the client side. So now we talk about server models. That's basically what her question is about. Is what type of server are we talking about? This is a lot of text, but what the end result is the call called select. It looks completely harmless. It doesn't even seem to have anything to do with file operations. Select what? What select does is it allows you to specify and say, okay, I have file descriptors, let's say 10, 11, 12, 13, all the way up to 100. Okay, so I have 91 open file descriptors, each one corresponding to a connection to a particular client. I have 91 connections. What select does is it allows you, to specify and say, oh, go ahead and monitor all 91 file descriptors. Okay, and you can specify which one to monitor for pending read operations, like, oh, something is ready, you can read it now, or ready for write operations. So now you can specify with these particular connections, I want you to monitor if anything is ready for me to read, unblock the select call. On these particular file descriptors, I'm trying to write to the client, but the client is really slow. I cannot feed the pipe. The pipe is not fast enough. Okay, so when it is ready to accept some more writing, let me know. So what you're doing is you're using the select call to tell the kernel and say, wake me up when there's work that I can do. So when select returns, it means at least one of the things that you're waiting on has something you can proceed with that. Are we doing okay so far with the concept? And select will actually return and tell you exactly which file descriptor can have work done at this point. In other words, it can tell you exactly, okay, FD file descriptor 23 now has at least 1 byte ready to read. You can now read that byte and process it. It can tell you file descriptor 64 is now ready to at least, you can write at least another byte to that file descriptor. That is how you handle multiple client connections with a single threaded program. But this only addresses the low-level part. Okay, how do we handle the coordination of all these different connections, all occurring at different speeds? It does not tell you how to structure your program. The question now is, how do you structure your program?
You're hanging on select until select tells you something, and then you have to it's going to tell you what file description needs processing, and then you're going to have to branch it out.
Has anyone heard of the term called finite state machine, FSM, which is also the abbreviation of the flying spaghetti monster? I always got those two confused. Yeah. Okay, a finite state machine is basically defining a machine, or in this case, a connection, to have multiple states. So when you write a program to handle multiple connections simultaneously, but using a single thread, a single process model, then what you have to do is to break up the handling of the protocol into little states. And each connection will have a data structure to remember what was the state it is in, so that next time when another byte comes in, it knows where to continue execution. So the handling of a particular protocol is no longer just sequential code anymore. It is now broken up into the finite state machines. A finite state machine is usually implemented by nested switch statements. Okay, do you still remember what is a switch statement? Okay, switch, case block, case block, case block, and then default. Okay, why is it a nested switch statement? The outer switch controls which state am I in at this point. The inner switch controls how do I get to the next state, and therefore it is it's a two-level switch statement. Or you can use conditional statement for that purpose. It is a lot of hassle. It can be done, and someone is going to ask, but is it really done in real programs other than homework assignments? There's a program called Squid. Does anyone know what is Squid? No? It's a web proxy, caching proxy program. Yeah, Squid. Yeah. And that particular program uses a single thread, single process model to handle multiple connections. It's a caching program. It's a proxy server caching program. So what that means is, okay, I can give you this example. This would be a good way to finish this class. Squid is typically what you use. Let's say Lost Reels or ARC has a Squid server. So that means when you want to go out to the internet to get something, a document like what we are reading here, it's not going directly to someprofs.org. It's going to the proxy server first. The proxy server will basically look up its own cache and say, do I have a local copy of this web page? If it does, then it will just grab it from its local cache and feed it to your browser. If it does not, then the proxy server itself will go out to the internet and go to some profs and then retrieve that particular web page. So what is the advantage of this two-step approach instead of my server going directly to some profs and grab that page?
I've considered this exact same thing for websites that I've done, and basically, if you get a web page that has content that is generally going to be the same all across multiple requests, it is much, much, much cheaper to run a Squid server that will essentially act as an intermediary and say, you don't need to bother the server about this, here's your answer.
Yep.
Instead of saying, okay, server, go through this process to determine what the response is going to be every single time.
Exactly. Now, for a small page like this, this page is probably really tiny, maybe in 1 or 2 kilobytes range. It's not a big deal. Go out to the internet, get a page. It's not really a big deal. But what if you're grabbing something that is like in the order of 500 megabytes? Then it starts to become painful. Yep, go ahead.
And even more so, what if you have tiny little pages that require a lot of server-side logic to determine?
Lots of simultaneous connections too. So that means, okay, let's say we're talking about this class here. And let's just say that I give you a new virtual machine image, which is a 1.7 gigabyte file. Okay? And also, let's say this is not in a classroom like this. We're in one of the classrooms where each one of you has a computer in front of you. So when I say, oh, by the way, I got a new image that all of you can download, every single one in the class will click that link all at the same time. So now we have 20 plus connections, each one trying to grab and download a 1.7 gigabyte file. Okay? It's going to be very slow. Even though the district has a fairly fast pipe to the internet, it's still going to be very slow. But on the other hand, if you have a caching proxy server, then all 20 connections to grab that 1.7 gigabyte file will go to the proxy server. The proxy server will say, oh, I can see there are 20 people trying to get the same file from that same URL. So the proxy server will say, okay, you guys just hold on, I will try to grab the file myself. And what Squid can do is to say, I don't have to grab the entire file before I start to feed the clients. Squid is capable of grabbing a portion of the file, little by little, and then immediately turn around and feed the 20 clients that are trying to grab that file, all at the same time. So assuming we have a fairly fast intranet here on campus, then the actual speed of downloading is just downloading one single file from the internet instead of 20 connections going out, each one trying to download a 1.7 gigabyte file. There's a huge increase of speed in that case. So if you think about that perspective, as the Squid program, if it is a single thread program, a single process, how can it do something like this? Having 20 connections from the clients and having one connection out to the internet, and grab a few bytes, a few hundred bytes from the internet resource, and then feed these 20 clients at the same time as fast as it can possibly go. That's the question that we are asking here. And select is at the heart of the Squid program. The first time I encountered this select call is when I tried to read the source code of Squid, and at the time I obviously have not taken a class like this. I have not taught a class like this, so I had to figure out how the select call worked, basically all on my own, and it was fun. Okay, so this is where we're going to stop today. On Wednesday, I'll actually have coding examples, so that way we can connect what we have talked about today to actual programs that you can write. So I'll give you actual sample code that works on Wednesday. See you next week.